Test Universe 3.0 comes with a new ribbon-based user interface that gives structure, flexibility, and a better overview to the working area. Managing views and creating customized layouts is much easier now. The new ribbon displays large recognizable icons that show all the functions of the test module. If you are working with small displays, use the Expand Minimize button to collapse the ribbon in order to create a larger working area. The Quick Access toolbar is located in the title bar of the application window and exposes a set of commands that are selected by the user. The customizable drop-down menu contains the available set of default Quick Access toolbar commands. Just choose the ones to be displayed in the toolbar. The test object hardware configuration and test operation settings are contained in the Home tab. Start, stop, pause, or clear your results by clicking on the corresponding ribbon button. You can also use F5 to start and F6 to stop the test. Point to the icons with the mouse to check the corresponding shortcut keys that execute a specific function or command. The View tab has been specifically designed to easily manage the views and customize the layout of the test modules. A default layout has been provided as a starting point, where you have the opportunity to drag, dock, merge, or split the different views to suit your needs. Window arrangements can be modified by dragging the splitter bar to resize the windows. Automatic rescaling provides optimum use of the working area. The layout is also automatically scaled when resizing the main application window. For more advanced changes, including the arrangement of tabbed views inside the panes, unlock the views from the Manage Views section and prepare to configure the overall layout of your module. Drag the pane of your choice onto one of the docking stickers. The pane will automatically adapt to the selected position. Note the difference between dropping the pane onto a field of the central docking sticker of another pane as opposed to one of the corner stickers. The docking sticker of a given pane allows you to locate external elements inside the pane itself. The stickers in the corners enable the complete workspace in order to place any pane at the indicated positions. Alternatively, move the pane wherever you like without docking it to a fixed position. The panes remain in a floating state, so they can be dragged outside the application and even grouped together. Each pane can be composed of more than one view. For instance, the right pane in the default layout comprises the phasor view, the impedance view, and report view. When moving any view type, you can use the central field of the pane's docking sticker to place it as a tabbed view inside the selected pane. To separate a tab as an individual pane or to drop it into another pane, grab the tab and move it onto a sticker. If your preference is to use the keyboard rather than the mouse, you may move the selected view in any direction using the cursor keys while pressing the Shift key. For example, looking at the default layout, we select the Report View tab located in the right pane. Now, we press the Shift key and the left arrow. The report view comes out of the pane to a central position. If we press the left arrow once again, the report view is inserted into the left pane together with the test view. To move the tabbed report view to the upper position inside the pane, press the Shift key and the up arrow. You can also use the submenu on each pane to split or merge the views at the indicated position. Once you have completed your customized layout, it can be saved for future use. To do so, expand the Apply submenu and click on the Save As option to make it available at any time. It is then possible to save multiple layouts, and each of them can be used for different purposes. For example, we can use this last layout for analyzing the test results and another one for setting up the module. Remember that you can always return to the default layout by selecting the default entry under Apply. You can also find the customized layouts that have been saved under the Apply section. Saved layouts can be exported and imported, allowing them to be used on different computers. Keep in mind that the last layout before closing a given module will be automatically saved and used as the starting layout when the module is reopened. Although the test modules share a common interface, the number of tabs and icons included in the ribbon can vary depending on each specific module. However, the Home and View tabs are common parts. Check out the specific video tutorials to see all the possibilities that the modules may have to offer you. Omicron offers a variety of CMC types depending on your application needs. Our devices differ, for example, in their output power, accuracy, and number of analog outputs. The CMC 356 can be taken as a general example for the CMC connections. The front panel integrates voltage and current generators that may vary depending on the CMC model. The generator combination socket routes three-phase voltages and currents to a single cable for easy wiring. An auxiliary DC source is available to supply power to test objects. 10 binary inputs are also available to measure and assess the response of protection devices, with 4 binary outputs being available to feedback information to the device under test. The rear panel of the CMC includes a USB and Ethernet ports for connection to the PC. The Ethernet ports provide the basis for the processing of substation protocols according to the IEC 61850 standard. The Associate button establishes a connection between the CMC and the controlling PC. Additionally, the external interface permits easy connectivity for meter testing, allows for GPS iRig-B synchronization, and holds 4 additional bounce-free binary outputs. Low-level outputs are included to control external devices like amplifiers. There are different options for controlling the CMC test sets. The Test Universe is a powerful test software suite that comprises several modules, including general-purpose and dedicated modules for specific protection functions and applications. All of them are standalone modules, meaning they can run autonomously. However, the test modules can also be embedded into an Omicron Control Center document, which allows users to create multifunctional test documents. This makes it simple to test a variety of protection functions within the same document. For instance, the document can contain a variety of modules, like a quick CMC module for the wiring check, distance modules to check the trip times, or state sequencer modules to test the switch-on to fault protection function. The power of Omicron software comes with the XRIO technology, which stands for Extended Relay Interface by Omicron. This feature allows the user to customize and compute parameter definitions for use in multiple test modules. Settings such as pickup values can be used as reference for calculations to automatically adapt input parameters to achieve automation within a testing program. These calculations can be as simple or as complex as the user desires. You can create a special custom block defining any parameter name, unit, value, or formula exactly as you know them from the test object. This way, you can import your test object parameters using a filter and link them to the test module input fields. We call this an XRIO converter. Because of the complexity of some protection devices, the task of designing an automated test file can be very difficult. Fortunately, Omicron can support all CMC users with its library of relay-specific test templates. The PTL, Protection Testing Library. Any customer can benefit from the PTL items that are freely available from the customer area on our website or from your installation DVD. PTL templates are completely open. Therefore, users can adapt a template to exactly match their needs. For special applications, the programming interface CM Engine allows users of CMC test sets to write their own programs. The programs can be created in common programming languages such as C++, Visual Basic, or LabVIEW to effectively interact with the functions of the Omicron test sets. As an alternative to using the PC for controlling the CMC, The CM control can also be used. The CM control is a front panel attachment equipped with an intuitive touchscreen user interface. This attachment is the ideal solution for portability and quick verification of test objects. The CM control can also be detached from the CMC and used as a handheld control device, or secured to the metal surface of the switchgear panel with powerful magnets contained within the CM control casing. Take control of the CMC with your Android-operated tablet. Visit the Google Play Store and download our latest application called the CM Control P app. The same test functions of the CM Control are permitted between the tablet and the CMC utilizing a wireless connection. This collection of video tutorials will focus on the Test Universe modules, beginning with the start page and then going deeper into its different features and applications. But first, an essential rule to keep in mind before attempting to start any test. This will make the life of a test engineer less challenging with regards to creating test files. Allow us to redefine the traditional electrical formula known as Ohm's law. We shall tweak this formula to describe it as Ohm's law according to Omicron. Ohm now represents test object, hardware configuration, and test module. The test object contains the information of the device under test. The inputs, outputs, and other specific signals are defined in the hardware configuration. Finally, operating the test module is when you perform the test. All this information must be completed before you conduct your test. We hope this mnemonic rule helps you remember how testing with the test universe should be conducted. Now we shall give you a short overview of the test object structure. To open the test object window in Quick CMC, click on the Test Object button. On the left side, you can see several blocks. The two main blocks are Custom and Rio. The Custom block allows you to create individualized blocks and parameters that you can customize freely. Rio stands for Relay Interface by Omicron and offers you a standardized format for modeling devices. The Rio block will always include a device block and maybe further blocks like distance or overcurrent, depending on the test module you are working with. The device block contains general information about the protection device, such as name, type, manufacturer, and a number of preset general parameters, such as nominal values, residual factors, or limits. In summary, it identifies the test object. Double-click on Device Block. You will see that the window is split into different sections. In the Device section, enter all the important information that is useful to identify your device. This information will appear in the test reports. Describe the location of the device in the substation and base sections. In the section of the window, you can set the nominal values of your power system network, including primary and secondary values for voltage and current and the frequency of the network. The test modules will use these values for calculation. The residual voltage and current factors section is only relevant if your relay has separate inputs for the residual voltage or current. Here, you can set the residual ratio in relation to the single phase ratio. An open delta connection has been taken by default, resulting in factors of the root of 3 for the residual voltage and 1 for the residual current. The limit section allows you to set a maximum voltage and current that must not be exceeded when testing the test object. These values are used by all test modules. The debounce and deglitch filters section allows you to set a filter on the binary inputs for bouncing contacts or to eliminate unwanted glitches in a noisy environment. The overload detection sensitivity section might be changed when you test high-burden electromechanical relays. You can get more information on the device settings by using the Context-Sensitive Help. Click on the Context-Sensitive Help button in the menu bar. Then click on the feature for which you need more information. The Omicron help system will display the exact information you need. Finally, the File menu contains the export and import commands. You can use them to save the test object settings for reuse with a similar test object or for reuse within a different test module. This tutorial will give you a short overview of the hardware configuration structure, which consists of up to 6 different tabs. The hardware configuration can be considered as an interface between the CMC and the module of the Test Universe software. Remember that the different types of CMCs have different hardware features. The hardware configuration enables you to define how you want to use the test set according to your specific application needs. On the General tab, the user can define the test hardware to be used. In the combo boxes, under the test section, the Omicron test sets are either displayed together with the serial number or can be manually set in offline mode. Click Details to change the voltage or current outputs configuration of the selected CMC test set. The illustrations on the right side of the configuration tables show how to connect the outputs with the selected configuration. The second section allows the selection of additional amplifiers, low-level outputs, or sensor simulations. Click on Details to set or change the configuration of your selection. Use the Import-Export feature to save or load the hardware configuration with the OHC extension. This way, the hardware configuration can easily be transferred to other test modules. The usage of the outputs and inputs can be defined in the following tabs. The number of available inputs and outputs will depend on how the test hardware has been defined in the General tab. All tabs are structured in the same way. Therefore, we can take the Analog Outputs tab as an example. The wiring matrix on the right allows you to indicate how the signals are connected to the CMC test set. This way, the first column assigns the output signal of the test module to the CMC test set output specified in the same line. This means that the voltage in phase A is assigned to the CMC output 1. The drop-down menu only displays the signals that a specific test module might need to conduct a test. The second column contains the names that will be displayed in the test module and test report. Finally, the labels of the test object connectors can be entered in the Connection Terminal column. If we have a look at the Binary Inputs tab, we can visualize the same structure, but with additional settings included. Most importantly, do not forget to indicate whether the signal is connected potential-free, which means dry, or with a specific voltage, which means wet. If the potential-free checkbox is cleared, both nominal range and threshold fields become available. Nominal range represents the nominal voltage of potential sensing binary or counter inputs, or the nominal range of analog voltage or current inputs. Threshold indicates the limit for potential sensing binary or counter inputs. Apply the same theory to configure the Binary Outputs tab. Finally, the Time Source tab permits the user to configure the trigger and synchronization setup for GPS, iRig-B, and PTP connections. Since the CMC test set can also work as an iRig-B generator, you can also use this tab to specify the timecode parameters. Quick CMC allows you to manually conduct different tests without having to pre-configure an automatic test plan. It is the ideal starting point for new users of the Test Universe software. Quick CMC is easy to use, powerful, and at the same time allows the user flexibility to test a wide range of devices, including overcurrent, differential, and distance relays. It can also be applied to testing transducers and meters. Quick CMC can be seen as a virtual front panel control. Voltage and current outputs can be defined statically in magnitude, phase, and frequency, which, for example, is good for testing overcurrent trip times. In addition, these signals can be set to ramp up or down, checking pickup drop-off settings, or even over/under voltage settings. Parameter settings such as trip times can be measured using the CMC binary inputs, and feedback signals can be created using the binary outputs. Omicron's Ohm's law, relating to object, hardware, and module, is a guide to follow for creating new tests easily. First, open the test object function to configure the relay under test and complete the entry fields on the Device Settings tab. Our relay is located in a 110 kV network at 50 Hz. The voltage transformer ratio is 110 kV to 100 volts, and the current transformer ratio is 600 to 1. The relay can withstand a maximum continuous current of 4 amps. The overload sensitivity is set to high for digital relays. We apply the default values for the filter function. You may wonder why QuickCMC contains a distance block when it is not a dedicated module for this specific protection function. This is because QuickCMC can use parts of the distance test object, like the impedance diagram or line angle, while testing distance protection. Now we can export this configuration for future applications. The second step to the Ohm's Law guide is the hardware configuration, where you define the hardware inputs and outputs you want to use for testing. In our example, we define a generic configuration with 3 voltages and 3 currents. We will assign the start and trip contacts to binary inputs 1 and 2. The last step will be the configuration of the module itself. QuickCMC is divided into several windows which are accessible via the View tab. In the Test view, specify all required test parameters. It is also split into different sections. The Analog Outputs drop-down menu offers a variety of fault modes to choose from. The default option is the direct mode, as it is the most common and simplest way to test with QuickCMC. Using direct mode, you can control the voltage and current generators by setting the amplitude, phase, and frequency of each generator. Define the settings by clicking on the field you want to edit and enter the desired value. On right-clicking the mouse, you can choose from a range of commonly used values from the context menu. This allows for a fast and convenient configuration of your tests. A typical application is to perform a wiring check by injecting some values of voltage and current using the direct mode. By observing these values on your relay's display, you can effectively check that the wiring has been connected correctly. The test view also includes a phasor diagram that displays the values entered in the analog outputs table. However, you can also set the values here by dragging the vectors. The binary outputs are activated by selecting the corresponding checkbox. To activate any of the 8 binary outputs, they must have been previously enabled in the hardware configuration. The Home tab is the main view for controlling and running a test. To start a test, the Start button should be activated and all defined output values will be injected into the test object. The test execution can be stopped automatically in the event of a defined trigger condition, such as a binary input trip command. If you want to start your test with a pre-fault condition, click on the Pre-fault button. This will generate a healthy network condition of 3-phase nominal voltage. There is an option to hold the test outputs at their set value by pressing the Hold Values button. While this button is enabled, the CMC output values are held while new output settings can be set on the Analog Outputs table. Releasing the Hold Values button will then inject the new values into the test object. This is useful, for example, if you want to switch from a healthy network condition to a 2-phase or 3-phase fault. The Analog Inputs section displays the measurements of the transducer inputs. The Binary Inputs and Trigger section displays the status of the binary inputs to the CMC test set. The number of available binary inputs is defined in the hardware configuration. The LED icons display the operating state of the 10 binary inputs. Red indicates that the binary input is active. Each individual binary input can be defined as a trigger by activating the checkbox. The trigger determines which binary input starts the timing measurements. Once the trigger occurs, the binary inputs and trigger box display the slope of the signal change, rising or falling edge, and the time that elapses between the latest change at any of the CMC outputs and the state transition of the binary input. Selecting Switch Off turns off the CMC analog outputs the moment a trigger signal occurs at the binary input. Since Quick CMC does not do any automatic assessment, it is necessary to click on the Add to Report button to transfer the settings and results to the report. Click on the Report view to access the report containing all tests. Any change in the test object or hardware configuration is not allowed unless all results are cleared first. As explained in the first clip, there are various set modes available to output the voltages and currents in Quick CMC. For example, symmetrical components or powers. The phasor view is very useful if you are not working in the direct mode, but in one of the other set modes. The main function of this window is to show the actual outputs of the CMC generators. Having the phasor view activated and set to the Output Values mode is therefore strongly recommended. By right-clicking on the phasor view, you can always switch to other display modes to show calculated components in relation to the values you set in the test view. The impedance view window is only relevant if you choose one of the impedance set modes in the test view window of Quick CMC. In this case, the impedance view shows you the fault impedance that you have set in the analog outputs table, but you can also set the values by clicking on the impedance plane. The characteristic shown in the impedance plane is taken from the data set in the test object. The step and ramp functionality in Test View lets you increase a certain quantity to perform basic pickup, drop-off, or trip time testing of all protection functions. Depending on the selected set mode, you can ramp relevant quantities including voltages, currents, powers, and impedances. Use the Signal and Quantity drop-down menus to set the combination of your choice. The selected output quantity can be ramped in two ways, manually or using the Auto Step option. To ramp manually, you can either use the up-down button or the mouse wheel to increase or decrease the output values by the defined step size. To ramp automatically, select the Auto Step checkbox. To start the ramp output, click the up-down button first. The output values are now automatically increased or decreased according to the defined step size and time. Note that the signal step time cannot change more quickly than 100 milliseconds from one step value to another. The ramp will stop when the trigger condition is met or when the up-down buttons are clicked again. Once a ramp is stopped, the last generated ramp value is held and statically output till the CMC stops the injection by manually releasing the start button or using the automatic switch-off option. Select the pulse ramping option when testing the values of a multifunctional protection relay with overlapping characteristics or functions. A pulse ramp inserts a reset state in between two consecutive ramp pulses. In this way, for example, the second element of an overcurrent protection can be tested. This is of particular use as we do not need to deactivate the pickup function of the relay. In terms of functionality, pulse ramping only works when the Auto Setup checkbox is selected. This video tutorial will teach you how to use the ramping module of Test Universe. This module determines limiting values of protection functions like the overvoltage or under-frequency pickup by generating ramps through the CMC test set. Ramping is able to perform an unlimited number of measurements, which are automatically assessed according to user-defined tolerance parameters. In this video, we will be testing the pickup value of our relay's emergency overcurrent protection function. Going back to the OCC file, we insert a new group called pickup values, which will contain the ramping module. To make the procedure easy to understand, we will support our explanation with the following figure, which includes all the parameters required to perform the test. The relay's pickup value has been set to 1.8 amps and is signified by the blue line. According to the relay's manual, the pickup value has a tolerance of 3%, determining both upper and lower limits that are represented by green lines in the figure. The goal of this test is to check that the pickup value is contained within the tolerance band. Now it is time to define the start and end values of the ramp. This way, you are free to choose any value as long as you ensure that the ramp will cross the entire tolerance band. However, just to give you an easy rule to follow, our advice is to start at 0.8 times and end at 1.2 times the nominal value. The calculated values are 1.44 amps and 2.16 amps. That said, we can proceed to complete the fields with these values. But before going any further, we have to check our test object and local hardware configurations according to Omicron's Ohm's law. Regarding the test object, there is no need to make any change. For this specific test, we just activate 3 currents and the start contact in the local hardware configuration. No binary outputs are required. Like the other modules, the ramping module comprises several views. At first, in the ramping's test view, you can select the shape of the ramp by adding states and setting the individual ramp parameters. Like the other test modules, you can define the set mode. 2 functions of any signal combination can be ramped simultaneously up to 40 ramp states. In this example, we will use 2 states to ramp a combination of 3-phase current magnitudes in direct mode. The first state will be used to ramp up and the second state to ramp down. According to our previous figure, the starting point of the ramp will be 1.44 amps, while the end point is 2.16 amps. For the second ramp, we just enter the same values. The steps are defined by the time and delta magnitudes. The amplitude of delta is a compromise between accuracy and test time. The bigger it is, the less accurate and shorter the test time. If you choose a value bigger than the tolerance band, the resulting measurement will be of no use. As a reference, we recommend that you take the tolerance divided by 4 as delta magnitude. That is, 3% of 1.8 amps divided by 4, which makes 14 milliamps. The time is the period between 2 ramp steps. This duration must be longer than the operating time of the relay. Since the pickup is estimated by the relay's manual to be 30 milliseconds, the step time has to be greater than this value. Therefore, 100 milliseconds will suffice. We apply the same settings for the second ramp. Out of these values, The number of steps and the total amount of time for the test is calculated automatically. The total number of steps indicated here is the maximum number assuming that the ramp is not stopped by a trigger condition, and as a result, it reaches the end value. The total time represents the number of steps multiplied by the step time. The stop condition displays the ramp state's trigger condition. This condition is set in the detail view. The detail view window has three separate tabs. In the first tab, called Analog Outputs, you can set the static values of the non-ramped analog CMC outputs. This is why the ramped values are grayed out, as seen in the fields that contain the three current magnitudes. In this case, only the phase and frequency components can be modified. In the second tab, you can activate or deactivate the CMC binary outputs. However, these outputs are disabled on the hardware configuration since there is no need to apply them in this example. Finally, the third tab will set individual stop conditions to terminate the state before it reaches its end value. The default setting is None, that is, no trigger will stop the ramp state. It runs from 1.44 amps to 2.16 amps. The key pressed option enables you to manually trigger the ramp state termination during the test. When the ramp starts, a dialog box will pop up and wait until you press continue. The binary trigger can be any single binary input of the CMC or a logical combination or multiple binary inputs. The logic functions and or are available for that purpose. In the binary trigger condition box, you need to specify the binary inputs you want to use. In our example, the first state must stop when the start signal switches to 1, while the second state must stop when the start signal goes back to 0. Note that the detail view needs to be configured for each state. Toggle from one state to the other by clicking the arrows from the ramp navigation toolbar or directly selecting the specific state. Once the ramp parameters are set, it is possible to specify measurement conditions for automatic assessments. Also, ramp calculated assessments are available. Toggle from one to the other in the View tab. An unlimited number of measurements can be performed. If we have a look at the ramp assessments table, we first need to enter the name of the measurement. We strongly recommend that you use the name that best reflects what is actually measured. For example, pickup and drop-off. The ramp column shows the ramp state in which the measurement is performed. The pickup will take place in state 1, while the drop-off will take place in state 2. The condition column reflects the condition to start the measurement. We will measure the pickup value when the start contact switches to 1 and the drop-off value when switching to 0. The nominal value is the expected value, 1.8 amps for the pickup. According to the relay's manual, the drop-off value is around 0.95 times the pickup, which makes 1.71 amps. The deviation contains the allowed tolerance values. As explained before, the tolerance is 3% in both directions, positive and negative. 3% of 1.8 amps makes 54 milliamps. We can keep the same value for the drop-off deviation. The rest of the columns display the actual values after the test is performed. In the Calculated Assessments table, we can define calculations of signal relations, for example, the pickup to drop-off ratio. The nominal value will be 0.95 according to the relay's manual. Normally, you do not find any tolerance of this ratio in the manual, so we can keep the default value of 5%. Now, the test is ready to be performed. Finally, all parameters have been set, and we are ready to do the practical test. By clicking on the play button, we can run the test and see what the result of the measurement is. Now, we see the relay picked up and dropped off within the allowed deviation. It is therefore assessed with a green cross. The actual drop-off ratio has also been assessed as passed. After running the test, we can also have a look at the signal view that shows the ramp states with the recorded binary inputs. We can see the ramp starts at 1.44 amps and stops when the relay picks up. After the pickup, the second state begins to ramp down until the relay drops off. The drop-off signal cannot be appreciated at first sight unless we zoom in. Go back to the normal view by optimizing it. Always have a look at this view to check the shape of the ramp and the recorded binary inputs. This is the best way to ensure that the test has been performed correctly. This tutorial will show how to test the high set of an overcurrent relay with two elements. The pulse ramping module has been specifically designed to test the pickup value of protection relays with more than one element. Pulse ramping means that the current is not increased continuously, but in a sequence of short pulses, to prevent the first element from tripping. As shown in this figure, the first element trips at 1.8 amps with a delay time of 500 milliseconds. The second element trips at 6 amps with a delay time of 100 milliseconds. The idea of testing the pickup value of this last element by continuously increasing the current will fail to work because the first element will always trip before reaching the second element. By ramping the current in pulses shorter than 500 milliseconds, it is possible to prevent the first element from tripping and gradually approach the second element. To do this, we insert a new pulse ramping module in our OCC file and we apply Omicron's Ohm's law. Since we are testing the high set of the overcurrent protection function, we need to increase the maximum current allowed in the test object. Otherwise, it will not be possible to reach 6 amps. Regarding the hardware configuration, we activate 3 currents and the trip contact. It is not possible to use the pickup contact because this signal will be active at any time after reaching the first element. None of the other signals are needed. The test view window is composed of 3 tabs. The first tab, Ramp Parameters, contains the parameters of the ramp and the measurement conditions. The signal and quantities to be ramped need to be selected from the drop-down menus. In this example, we will simulate the variation of magnitude in a 3-phase fault. Similarly to the ramping module, the ramp signals are disabled in the fault state table. With regards to the ramp settings, a pulse ramp always starts with a pre-fault state in which the reset values are applied. Since the duration of this state is not critical in this example, we can keep the default value. The pre-fault state is followed by the first pulse that starts at the value indicated in the from field. The pulses will be increased by delta until the end value is reached. To determine these settings, we will follow the same theory that we recommended in the ramping module. The ramp will range from 80% to 120% of the high set value. As delta, we will take the current tolerance from the manual divided by 4. Then, the start value will be 4.8 amps. The end value, 7.2 amps. And delta, 45 milliamps. The rest of the parameters to be output during the pulses can be defined in the fault state table. Balanced angles and a frequency of 50 Hz are set. The fault state must be shorter than the trip time of the first element, but it must last longer than the trip time of the element you want to test. Therefore, it has to be a middle ground between 100 and 500 milliseconds. Let's say, for example, 300 milliseconds. In order to measure the high set, the reset value must permit the relay to drop off. The reset state will be applied in between two pulses during the reset time. To avoid any confusion, the current has been set to 0 and the duration to 100 milliseconds. This is long enough for the relay to drop off between two pulses. In the assessment section inside the test view, the measurement conditions can be defined. First, the contact to be monitored, in this case, the trip contact. Then, the nominal value and tolerances. The expected pickup value is 6 amps. To enter the tolerances in percentage, check the relative tolerance box, in our case, 3%. The pulse ramping module will automatically assess the test results using these values. Have a look at the state phasor view to see a graphic representation of the settings made for the reset state and fault states. Switching to the binary outputs tab, the conditions of the binary outputs for the reset state and the fault state can be determined. In the General tab, we can define how the test should be started and stopped. By choosing Immediately, the test will start as soon as the Start button is pressed. The binary input option starts the test by the occurrence of a trigger signal at a selected binary input. The last option is used for GPS-synchronized end-to-end testing. For this test, Immediately will be the starting option. This checkbox lets you decide whether the ramp should be stopped if the measurement condition is reached, and here we can set a delay time for the stop. Start the pulse ramp by clicking on the Start button. Check the Time Signal View window to visualize the pulse ramp or the recorded binary inputs, and the Report view to see an automatically generated report of the test. The State Sequencer module has been designed to provide a flexible automated tool for testing. A complete sequence of states can be defined and measurements can be assessed automatically. The State Sequencer's interface has been structured in the same way as the other modules. The table view summarizes all defined states. Use the States tab to create, delete, or navigate between states. You can configure the states in the Detail View window. For example, the Analog Outputs tab allows you to set the voltages and currents in one of the fault calculator set modes. The Binary Outputs tab is used to define which of the binary outputs will be active in a particular state. Remember that this tab will only be visible when the binary outputs are enabled in the hardware configuration. The Trigger tab defines the condition that terminates each state. There are different possibilities: maximum state times, binary trigger conditions, manual user interaction, and external triggers like GPS or iRig-B pulses. Use the Assessment section to define time measurement conditions and evaluate binary conditions during the states. After this introduction, we are ready to build an application example with State Sequencer. For example, we can test the first element of our relay's emergency overcurrent protection function, which is set to 1.8 amps with a time delay of 500 milliseconds. First, we enable three-phase currents and the trip contact in the local hardware configuration. The test object parameters stay the same. The goal is to simulate two fault events just before and just after the boundary of the first element to measure the relay's reaction. It is advisable to draw a workflow containing the states and trigger conditions to be implemented in State Sequencer. Our sequence will be composed of an initial pre-fault state with a timeout of 1 second. This state will be followed by a three-phase fault state at 90% of the first element setting, that is 1.62 amps. The relay is expected not to trip, so the state's termination will be set to a 1 second timeout. Next, we add two additional pre-fault and fault states, but this time the simulated fault will occur at 110% of the set value, that is about 2 amps. The termination of the fault 2 state will be a combination of a binary trigger and a timeout. This means that the next stage will begin as soon as one of these two conditions, whatever occurs first, is fulfilled. This way, we force the module to move on to the next state in case the relay doesn't trip. Finally, we add a post-fault state with no current to finish the sequence. The timeout is set to 1 second. Now, we use the States tab to add 5 states to the table view. The next step is to assign names to each of the states. For example, pre-fault 1, fault 1, pre-fault 2, fault 2, and post-fault. Going to the detail view, we enter the output values and define the trigger conditions for each state. We start with the pre-fault 1 state. The current to be injected is 0 amps, while the timeout is 1 second. The fault 1 state consists of a three-phase fault with a magnitude of 1.62 amps. The timeout is 1 second. In order not to bore you, we will complete the remaining sequence of states by following the same procedure. Remember to select both the timeout and binary trigger condition in the fault 2 state. Once the binary trigger condition is selected, you need to specify the signal state. The trip signal has been set to 1, which means that the state will terminate if the relay trips. We can use the time assessment table to measure the recorded trip signal during fault 2. The measurement will then start at fault 2 and will end when the trip signal is detected. Since more than one trip may eventually occur during the sequence, the Ignore Before option allows the user to narrow the search by ignoring any event before the state indicated. In this case, we will ignore any trip signal before fault 2. The nominal value is 500 milliseconds with a tolerance of 40 milliseconds. In state assessments, you can define the binary signals which have to be present or not during the states. The tolerances define the time range after the beginning of a state during which the signals are permitted to deviate from the defined conditions. State assessments can be used in this example to check that the relay does not trip during the fault 1 state. Finally, we are ready to run the test and check the measurements. The green crosses indicate that the trip time fulfills the tolerance requirements and that no trip occurred during the fault 1 state. Don't forget to check the Time Signal View window to have a graphic overview of the sequence and the recorded signals. Here, we can confirm that the relay tripped because of the fault generated during the fault 2 state. The overcurrent test module is used for the automatic testing of directional and non-directional overcurrent relays with auto-assessment of the trip time characteristic and directional boundaries of the current stages. This module supports directional sector definition and any number of line, ground, positive, negative, and zero sequence elements. The overcurrent module also allows for the testing of the pickup and drop-off values and reset ratio. As we are using this module to test the trip time of the overcurrent protection function, we can proceed to create a new folder called Trip Times in our OCC file. After inserting the module in the folder, we first need to check the test object according to Omicron's Ohm's law. Since this is a dedicated module for overcurrent relays, a new specific block appears in the text object's menu. This new block stores the necessary data about the relay's overcurrent protection function and must be completed. There are two tabs, the first one for general settings and the second for defining the trip time characteristic. In the Relay Parameters tab, you can select the directional behavior of the relay under test. When directional is selected, the options for VT and CT connections are enabled. The VT can be installed before or after the circuit breaker. Select at Protected Object when the VT is installed after the circuit breaker. Select Not at Protected Object when the VT is installed before the circuit breaker. The same theory applies for the CT connection. Select To Protected Object when the CT start point is connected on the line side. This means that the currents generated by the CMC test set are in phase with the currents that the primary network would have. Select From Protected Object when the CT start point is connected in the busbar side. In this case, the currents generated by the CMC have a 180-degree phase shift compared to the currents that the primary network would have. Enter the current and time tolerances according to the relay's manual. These tolerances can be defined as either absolute or relative values. Relative is a percentage of the setting value. Absolute is a constant value that is defined as a multiple of the reference current. The reference current is linked to the nominal current by default. The Elements tab is used to define the tripping elements of the relay. Test Universe supports different element types: phase, residual, positive sequence, negative sequence, or zero sequence. Each element type can integrate several tripping elements. Add the element type of your choice and configure the settings on the Define Element Characteristic tab. Click on the Browse button to get access to a list of standard predefined and user-defined characteristics. Among others, you can use define time or inverse characteristics and adjust the parameters at your convenience. The characteristic to be tested can be restricted in the Range Limits section. Testing characteristics with a minimum tripping time is a typical application example for this feature. It is also possible to define definite or inverse time reset curves to test a relay with a reset characteristic. If the relay behavior has been set to directional in the Relay Parameters tab, a new tab will be displayed to enter the corresponding data. The trip sector can be defined by its start and end angle or by its direction and sector opening. The blinder can be used to cut a part of the trip sector. A compiling graphic including all the elements and the directional behavior is displayed in the View Resulting Characteristic tab. To keep all these concepts in mind, we will proceed by configuring the overcurrent block according to the relay we are testing in the OCC file. That is, a non-directional relay with two definite time elements. First, we set the behavior to non-directional and we enter the corresponding tolerances of time and current. In the second tab, we choose a phase element type from the drop-down menu and we add 2 elements. Then, we browse and search for definite time characteristics. The values for the pickup and trip time can be entered for each element. The first element trips at 1.8 amps with a time delay of 500 milliseconds. The second element trips at 6 amps with a time delay of 100 milliseconds. No range limits or reset characteristics are specified. Finally, we check if the data we have entered matches the resulting characteristic. Before we walk you through the module, do not forget to check the local hardware configuration. Since we will measure the trip times of the overcurrent protection function, the currents in all 3 phases and the trip signal will be enabled for this test. In essence, the overcurrent module presents the same layout and views that we already know from the other modules. Therefore, we start off with the test view. Since no binary outputs are used in this example, we can jump directly to the Trigger tab. Test Universe needs to have a time reference and a trigger condition to do the assessments. The trip time can either be measured from the fault inception to the trip signal or from the start signal to the trip signal. The table in the trip condition section displays all the CMC inputs that are routed in the hardware configuration. Here, you specify which binary inputs are used to measure the trip time. In this example, we will use the fault inception as a reference for measuring the trip signal. It means that the measurement will include the pickup time. The Fault tab contains the settings that are necessary for performing the test. The Load Settings section allows you to supply current during the pre-fault time. Depending on the fault type that is simulated during the test, the load current could also be applied in addition to the currents in the fault state. Refer to the manual for more details about fault types. During the post-fault time, the load current is always off. The magnitude of the load current can be specified as an absolute value or as a multiple of the fault current. The phase angle of the load current can be the same as the fault angle or can be specified by the user. Use this decaying DC option to avoid magnitude jumps on the transition from the pre-fault state to the fault state if the load and fault angles have been set to different values. There are 2 ways to set the maximum time for the test point when no tripping is detected. Absolute and relative. The absolute time is a constant and independent value. The relative time is a percentage of the maximum trip time, which can be obtained from the tripping characteristic and the time tolerances. Test Universe always uses the smaller of these 2 time values. For the sake of simplicity, no load current will be injected in this example. The absolute maximum time can be set to a reasonable value, let's say 5 seconds. The relative maximum time can be kept to the default value of 100%. In the voltage settings section, you can apply a specific voltage to the faulty phase during the fault state. Since the voltage is essential for determining the fault direction, this option is selected automatically when testing directional relays. For testing non-directional relays, you can clear this box to disable this option. Now that the settings are already entered, it is time to define the test points for the characteristic test. This is done in the second tab called Characteristic Test. First, choose the fault type and enter the magnitude and angle of the fault currents. It is possible to enter the magnitude with absolute values or relative to the pickup current of an element. If the test point is set relative to an overcurrent element, the magnitude will adapt to the changes of the pickup value of the respective overcurrent element in the test object. Note that the angle can also be modified when testing with voltage output. Now, click Add to add the selected test point to the test point list. We strongly recommend that the characteristic is tested by approaching the boundaries of the tolerances. These are the more critical points of the characteristic. This way, a total of 4 points can be added at 90% and 110% of each pickup value for a phase-to-ground fault. The IT diagram in the Characteristic Test tab displays the resulting combined characteristic curve of all tripping elements that are relevant for the selective fault type. All the test points are also included in the diagram. Check the phasor view to see the currents and voltages that are output on each simulated point and other calculated values like symmetrical components or powers. The time signal view shows a calculated signal preview. After the execution of the test point, this preview is replaced by the actual signals. This includes the analog output signals and the states of the binary inputs and outputs for the selected test point. Now, we are ready to run the test and check the results. The overcurrent module will check if the measured time falls within the minimum and maximum times according to the test object's tolerances. When the condition is fulfilled and the test points are assessed as passed, we can see that the green crosses are displayed in the table and in the IT diagram. Finally, we can have a look at the time signal view to check the trip signal for each test point. Test Universe provides users with 2 modules to test distance protection functions, distance and advanced distance. This video tutorial will go through the advanced distance test module since it adds more features to the basic functionality of the distance module. Advanced distance is able to test the most important parameters of the distance protection function, the zone ranges and the trip times. For testing the distance protection function of our relay, we can create a new folder called Distance Protection in the OCC file and insert a new module. Following Omicron's Ohm's law, we need to enter the required data in the test object with special attention to the specific block for distance protection. The distance block comprises 2 tabs, one for general settings and the other one for building the zones. The System Parameters section includes the impedance and angle of the line and the VT and CT connections. Although the impedances are usually entered in secondary values, the Impedances in Primary Values box allows you to enter the line parameters in primary values. Impedances are then converted to secondary values by applying the VT and CT ratios contained in the device block. The time and impedance tolerances are required for the test assessments. The tolerances vary depending on the relay and are specified in the manual. In both cases, the larger of the absolute and relative tolerances is used. The grounding factor compensates the effect of the ground impedance in phase-to-ground faults. Different ways of entering the factor are available for allowing direct input from the relay settings. Independent of how the factor is entered, the compensation of the grounding factor is calculated with the magnitude and angle mode by default. Check the Calculation with RE over RL and XE over XL box to do the calculations with real and imaginary parts. Some relays treat the arc resistance separately from the portion of line impedance. In those cases, do not forget to check the separate arc resistance box in order to match the calculations of your relay. Now, we assume that our relay is located in this network. Relays normally divide the protected area in different zones, which are associated with increasing trip times. The first zone has the fastest trip time, and the remaining zones are used as a backup for other relays in the network. That said, the length and angle of the protected line is 7.84 ohms and 64 degrees. We can keep the default tolerances and both the CT start point and PT connected to the line side. The relay uses the RE over RL and XE over XL calculation method for the grounding factor. The values for both ratios are 0.6. Now, we can draw the zones in the second tab. To do so, find the characteristic of the relay and apply the specific settings to it. In our example, we have 3 tripping zones, 1 extended zone, and 2 starting zones. Add the first zone to the table and specify the type. Select tripping for a normal tripping zone, starting for a starting zone, and extended to define a zone which is only active under certain circumstances, such as an extended first zone. Now, we will show you how to draw the first tripping zone. The rest of them can be drawn in the same way. The first step is to define the number of lines in the characteristic, that is, 5 lines. Add the number of lines and decide the way to enter the coordinates, Cartesian or polar. Each line needs 1 point and 1 angle to be delimited. Because the zones are defined in the relay in terms of the intersection with the real and imaginary axes, it will be easier to use Cartesian coordinates. This way, one coordinate will always be set to 0, while the other coordinate is the relay setting for the zone. The next step is to define the line angle direction, clockwise or counterclockwise. We will use a counterclockwise direction for all lines. According to these criteria, and based on the settings shown in this figure, we can enter the points and angles of each line. Please pay attention to how we define the lines in the following sequence. Once Zone 1 has been created, it is necessary to assign a trip time to it. The Copy and Append option helps to save time when editing new zones with the same shape. Just copy, append, and adjust the coordinates of zones 2 and 3 and the extended zone. The directional starting zone is defined by two lines, which are common to the zones we have already created. Create a new starting zone and enter the coordinates of the lines. Use the invert option to change the direction of any line if necessary. The non-directional starting zone covers the whole plane. Create a new starting zone without lines to define the whole plane as active. The final characteristic is captured in the Advanced Distance module for easy testing. As we did with the rest of the modules, we are now checking the local hardware configuration prior to testing. We will use this module to test zone ranges and trip times of the distance protection function. Voltages and currents are required to generate impedances. Therefore, the currents and voltages in all three phases and the trip signal will be enabled for this test. The Advanced Distance module comes with the same well-known views from other modules. The impedance plane captures and displays the zones defined in the test object. It is of particular relevance when it comes to performing the tests. Additionally, Advanced Distance includes the impedance time diagram, which displays the trip time of a relay as a function of the impedance in the real imaginary plane. The test view is composed of 5 tabs. The first 3 tabs, Shot, Check, and Search Tests, are different modes of testing. The last 2 tabs are part of the preparatory steps to ensure a successful test. The Trigger tab is used to set the trigger conditions of the binary inputs to which the relay contacts are connected. Our trigger will be the trip contact that we enabled in the local hardware configuration. On the Settings tab, there are 3 simulation models available in the drop-down menu: constant test current, constant test voltage, and constant source impedance. Constant test current should be selected when testing distance protection relays with a current pickup setting. This way, the test current is set to the specified value and the relay voltage is calculated using the defined fault impedance of the test point. The pickup value for the relay under test is 1.8 amps. Therefore, 2 amps is suitable in this case. For test points with a higher impedance than those corresponding to the nominal voltage, the test voltage can be raised up to the maximum value indicated in the Vmax field. For testing above this limit, either manually reduce the test current or apply the automatic adaptation of test quantities. This poses the risk of preventing the relay from tripping when the test current does not reach the pickup value. In the fault inception section, the phase angle of the voltage can be specified. We select Random to approach more realistic conditions. There is also the option to add a DC offset transient behavior. The load current setting is meant to verify the exceptional behavior of certain relays that react differently if there is current present during pre-fault. As this is unknown for the relay under test, there is no need to activate this option. Each test shot consists of 3 states: pre-fault, fault, and post-fault. The time for each state can be set in the time section. As in the overcurrent module, the reference for the time measurement can be set to the fault inception or the pickup of the starting contact. Activating the extended zones makes these zones available for testing and will be displayed in the impedance plane. Of course, the relevant zones must be defined as extended zones in the Zone Management dialog box in the test object. The switch off at zero crossing causes the CMC test device to disconnect the currents after tripping in the corresponding natural zero crossing. The accuracy of the search test is determined through the search resolution fields. The larger resolution of either the absolute or the relative search resolution is applied. The search for the actual reach impedance stops when the difference in impedance between two consecutive shots is less than the given search resolution. If the characteristic is unknown, check the Ignore Nominal Characteristics option. In this case, the algorithm changes and the shots are placed at fixed search interval distances throughout the search line. The Advanced Distance module is able to perform 3 different tests. The voltages and currents to be injected are automatically calculated based on the module settings and test points. The shot test is able to apply multiple test points to check zone reaches and trip times. As a result, the measured trip time will be displayed and a comparison of the nominal and actual values can be performed in the application of the relay tolerances. For example, we can check the trip times of each impedance zone for phase to ground faults. After choosing the fault type, there are 2 options available to add points to the table. You can either use the test point section to enter the coordinates in absolute values or relative to the nominal zone reaches, or right-click on the impedance plane to add a test point of your choice. Although it is possible to simulate different fault types within the same test file, we strongly recommend that you use individual modules to test each fault type loop. In case the test fails, you can avoid an unnecessary repetition of those fault types that have been assessed as passed with a green cross. There is an option for quick check of test points without report or entry to the test table. Locate a test point in the impedance plane and press the Single Test button or select the Shot At option by right-clicking on the impedance plane. The check test is also meant to check the reaches and trip times, but with a slight modification. In this case, check lines are defined. Along these lines, the test module automatically places test shots outside the tolerance band whenever a line intersects with a tolerance border. Therefore, a positive assessment proves that the zone reach is within the tolerance band. Finally, the search test can determine the exact reach of the individual zones by applying several shots along a search line. Note that this test requires multiple test points to be applied in a sequence and might affect the performance of certain types of relays, for example, old electromechanical relays. Both check and search lines can be defined by the origin coordinates, the line angle, and the line length. The line length can be entered in absolute or relative values. However, an easier way to do this is by drawing the line directly on the impedance plane. For each zone, you should check the resistance, reactance, and line angle. This can be done by placing a line along the real axis to check the resistance settings. One line at 90 degrees to check the reactance settings, and one line parallel to the real axis to check the line angle. It is also advisable to place one additional line along the line angle to check the operating area of the relay. In any case, try to avoid corners. In addition to this, you can use the Sequence tool. Here, you can define a sequence of check or search lines for any fault type of your choice. All lines have a common origin point and the same angle step size. The number of lines depends on the start and end values as well as the angle step. Once the test entry fields have been successfully completed, we are ready to conduct the practical test. Use the Start Continue button to run the complete sequence of tests. Use the Impedance Planes context menu to customize the graphic setting according to your needs. Adjusting the zoom, adding a grid, or hiding elements are some of the options available. Do not forget to analyze the information contained in the table. The measured trip time in conjunction with the tolerance settings can be useful to identify any problem when the test fails. The test points of the check and search tests are displayed using the same status icons as the shot test. The progress of these two tests can be monitored since the check line currently being tested is highlighted. Each line is shown as one individual entry in the table. For further details, you can always use the impedance time diagram to analyze the particular test points of the selected line. The impedance time diagram displays trip times as a function of the impedance. Check the report view to see all the information that has been gathered. Remember that you can always modify the content to meet your special requirements. For example, you might be interested in adding the impedance plane diagram to the report. Most of the faults in overhead systems are arc faults caused by temporary conditions. Often they disappear automatically when the line is disconnected. Therefore, the use of automatic reclosing is usually advisable. Auto reclosing can minimize the disconnect time resulting from electrical faults. In the graphic, you see the signals for the automatic reclosing. When a fault is detected on an open line, the relay trips and the line is disconnected. Once a dead or delay time has elapsed, the line is automatically reconnected. If the fault persists, the line is disconnected again. Depending on the number of reclosing cycles, the line will remain disconnected or a renewed attempt will be made to reclose the line. To test the auto reclosing, we insert the auto reclosure test module in the OCC file. In this example, we will test an automatic reclosing with only one reclosure cycle. But remember that you can test up to 15 cycles in the test module. According to the relay under test, the extended zone Z1B is enabled before the first auto reclosure. This means that the relay trips instantaneously for faults up to 120% of the line impedance. Now we start out with the local hardware configuration. The voltages and currents are required for this test. Additionally, we need the protection relay's trip command and the circuit breaker close command. In the first tab, you can define the fault settings. In our example, we will simulate a fault within the extended zone so we can check whether this zone is active or not. Therefore, we choose the impedance set mode with constant current so we can locate the fault at 100% of the line impedance. We set the fault angle to the line impedance angle, that is 64 degrees. We can also use the link to line angle option. If you change the line angle in the real block distance of the test object, the fault angle will adapt automatically. Remember that the test current must be above the pickup value of the distance protection function. Here you can define the duration of the pre-fault state. This is useful when the auto reclosure function presents a blocking time after the last circuit breaker close operation. Then, the pre-fault duration must be greater than this blocking time. With the time limits during test, you can specify the maximum period of time that the module will wait for a trip or a circuit breaker close command respectively. Keep in mind that the time in the circuit breaker close entry field has to be higher than the dead time set in the relay. Otherwise, the test will be stopped before the relay sends the close command. The next tabs are the unsuccessful sequence and the successful sequence. These two tests are connected. It is only necessary to configure the test in the unsuccessful sequence tab, and the information is then captured into the successful sequence tab. If you are not interested in performing any of these two tests, just clear the box to disable it. The drop-down menu in the first column presents a list of possible events to be measured. In our case, the first event will be the trip. Regarding the assess mode, we take the time option. This way, we can enter the nominal expected time and the tolerances specified in the manual for an automatic assessment of the results. It is also possible to simply record the signal or to check whether the signal is detected or not. The second event is the dead time, which is set to 500 milliseconds in our relay. An unsuccessful sequence implies that the fault is persistent, forcing the relay to trip again. In our relay, the zone 1B is deactivated after the auto reclosing to ensure selectivity in the network. Consequently, a relay located at bus bar B is able to trip in the event of a fault beyond this location. For this reason, we expect our relay, which is located at bus bar A, to trip at the time of zone 2, that is, 400 milliseconds. Because we are testing one auto reclosure cycle, no CB close is expected after the second trip. If we take a quick look at the Successful Sequence tab, we can see that all the settings are taken from the Unsuccessful Sequence tab automatically. Naturally, this sequence does not include a second trip event. In the Assessment Settings tab, you can enter the start and stop conditions for each measurement. The definition of the dead time might depend on the relay. For some relays, the dead time starts when the trip signal goes from 0 to 1. This suits the relay under test. For some others, it starts when the trip signal goes from 1 to 0. The stop event happens when the close command goes from 0 to 1. When the test is started, the module begins with the successful sequence and proceeds with the unsuccessful sequence next. After the test is completed, you can check the associated time signal view for each sequence. The following tutorials will teach you how to test a differential protection relay with the advanced differential test modules. As an example, we will test a Siemens 7UT613 differential protection relay. In this tutorial, we will cover the test object and the global hardware configuration. You can test a differential protection device with the differential test module or the advanced differential test modules. Since the advanced differential set offers more features, we will use these modules to test the differential protection device. For testing the Siemens differential relay, we will make use of a new OCC test document. The four advanced differential test modules are diff configuration, diff operating characteristic, diff trip time characteristic, and diff harmonic restraint. We insert these four modules into the OCC document. According to Omicron's Ohm's law, we start with the test object. Fill out the entry fields in the Rio block device first. In our example, the protected object is a transformer. The CT ratio data is not relevant here since it has to be entered into the Rho block differential for all windings. The Rho block differential requires a lot of information, but once you have completed it, the testing of differential protecting becomes easier since all advanced differential test modules make use of the same Rho block. The differential block contains 5 tabs. The first one is the protected object. The second one, the CT. In the third tab, you enter the information about the protection device. In the fourth tab, you draw the characteristic, and in the last tab, you enter the characteristic of the harmonic restraint. We start with the information about the protected object. In our example, the protected object is a 3-winding transformer. In the picture, you see its nominal values. Now enter the nominal values of the windings, including the vector group and the star point grounding. In our example, the vector group is YYND5, so the star point of the secondary winding is grounded. The nominal currents are calculated automatically from the power and the voltage values. In this tab, you enter the data of the current transformer. In the picture, you see the values of the CTs in our example. The star point of the CTs can be grounded towards the protected object or towards line. In our example, all star points are grounded towards the protected object. If at least one winding of the protected object is grounded, you can check the Use Ground Current Measurement Inputs box. Then the residual current will be generated on the configured output. Remember to enter the information about the ground CT nominal values. The Protection Device tab is where you enter the relay settings. Set the formula for the bias current calculation according to the relay manual. If you have no access to the manual, check the Test Universe help to see which bias current formulas are commonly used by the different relay manufacturers. We choose the formula for our Siemens relay with a factor of 1. The maximum test time restricts the time for each shot to protect your relay. The delay time is the time in between consecutive test points. It is used to give the relay time to reset. Next, we have to specify the current settings. Therefore, we have to look how the characteristic is built. Small differential currents are also possible under healthy conditions. They exist due to transformer magnetization, tap changer, leakage, and saturation effects. The addition of all these effects represents the maximum differential current that is possible under healthy conditions. The differential characteristic is an approximation to all these effects. In our example, the characteristic starts at the low set value, which is 0.25 times the nominal current. It rises to 6 times the nominal current, which is the high set value. Above this value, the relay always trips independent of the stabilizing current. Input these two values, low and high set, in the entry fields. Consider the operating time for the particular relay when it comes to specifying the time settings. Check the manual and enter the tolerances for the operating time and the differential current. The output values are calculated based on the reference winding and the reference current. Note that these settings have to match the relay setting. This ensures that the differential and bias current values calculated from the relay are equal to the values visible in test universe. If you selected Protected Object Nominal Currents, the currents calculated in the first tab will be used as reference currents. If you select Current Transformer Nominal Current, the CT nominal currents entered in the second tab will be used. Depending on the network configuration, zero sequence elimination can be necessary in case of a single-phase fault. A typical case scenario is when a transformer is isolated in one side and grounded in the other. A fault outside the protected zone can lead to a false trip if no zero sequence elimination is applied. This way, the zero sequence components are subtracted so the currents at both sides are comparable. This operation may either be performed within the relay or by using interposing transformers. You have to specify if the zero sequence elimination is applied so that test universe adds the zero sequence component to the output currents if necessary. In other words, test universe reverses the relay's operation to ensure a perfect match between the calculated values from the relay and the test point specified in the test module. The Characteristic Definition tab is used to enter the characteristic. Each line segment is defined by its start and end points. Often these points are not given in the parameter set of the relay directly. Then you have to calculate them from the information available. The picture shows the points and slopes which are given in our example. From these values, we have to calculate the intersection of the lines by using the straight line equations. We get the 3 points required to define the characteristic in test universe. Check the Auto Init Start Point box to take the endpoint of the current segment as the start point of the next segment. The harmonic restraint characteristic can be defined in the Harmonic tab. You have to specify which harmonic component is subject to test. In this case, the harmonic restraint is activated for the second and fifth harmonic. The second harmonic is part of the inrush current that appears at the switch-on operation of a transformer. Enter the threshold for the harmonic restraint and define the tolerances. We keep the default value of 20% since it matches our relay settings. The fifth harmonic restraint prevents false tripping of the relay in the event of overexcitation. The threshold for this harmonic is set to 45% in our example. Click Update to validate any change in the entry fields. Our characteristics for the harmonic restraint are straight lines. If the characteristic is composed of several segments, you can enter the start and end points of each segment as we did in the Characteristic Definition tab. Now, confirm the dialog to save the information. The next step in Omicron's Ohm's law is the global hardware configuration. Since we are testing a differential protection, we need 6 current outputs, 3 for each winding under test. No voltage outputs are required. Name the outputs accordingly in the Analog Outputs tab. Regarding the binary inputs, only the trip command is required for this test. The diff configuration test module tests the wiring and configuration of the relay by simulating faults that are located outside the protected zone. If in such a test case the relay trips, this indicates a wiring or configuration fault within the protection panel. This video tutorial will focus on the configuration of the test module. Check the previous tutorial to see how the setup of the test object and the global hardware configuration is done. Before going any further, check the local hardware configuration to verify that the current outputs and the trip signal are enabled. The test view provides 4 tabs to parameterize the test. A single-line equivalent circuit diagram for the protected object is shown on the right-hand side. The binary outputs can be activated or deactivated from this tab. The General tab contains the information about the fault and the trigger conditions. For the sake of simplicity, this video tutorial will only show the test with regards to the primary and secondary windings. Remember, if you want to test the tertiary windings, you must add a new test module to the OCC document. The default setting here is fault primary supply secondary. However, we can locate the fault at the secondary side. The single-line diagram changes accordingly. For transformers with 3 windings, you can apply a load current. This load current is applied to the 3rd winding, as displayed in the single-line diagram. The use of the load current is not required by our relay. This test module gives you the option to check the readings from the relay and assess the results manually. The test time is the maximum period of time that the test current is output. Therefore, select a large enough test time that allows you to enter these values. Check the Apply Voltage box to enable the voltage output of the selected winding if necessary. To test a line differential protection, 2 or more CMC test sets can operate synchronized by a GPS, a PTP, or an iRig-B time reference. Choosing primary, secondary, or tertiary defines the currents to be injected when the CMC test sets are triggered. Choose the trigger condition. In this example, we just use the trip signal. A relay trip is not expected during the execution of this test. If a trip is detected, the diff configuration test module will automatically evaluate the test as failed. If no trip is detected, you have to assess the test manually. In the Test Data tab, choose the fault type and add the test points. The nominal current refers to the selected fault side, which is the secondary side in this example. The single-line diagram shows the resulting currents to be output by the CMC. The Test tab is where you assess the test. Select the values that you will read out from the relay. For example, the differential and the bias currents. Start the test and input the values measured by your relay. Since these values are correct and the relay did not trip, we can assess the test as passed. The actual values read from the relay will be saved in the report for full documentation. The Differential Operating Characteristic module tests the operation of the protection device for faults inside the protected zone. This video tutorial will show you how to configure the test module. Verify that the current outputs and the trip signal are enabled in the local hardware configuration. The test view displays the differential characteristic that you have defined in the test object. The General tab contains the settings of the test and the trigger conditions. First, choose the test method from the drop-down menu. In our example, we test from primary to secondary. You can apply a pre-fault condition for those relays that need to stabilize before the fault inception. There is also the ability to apply a voltage output if required. For end-to-end testing applications, it is possible to use a synchronized trigger. Since we want to test the operating characteristic of the differential protection, we use the general trip command as the trigger. Both shot test and search tests are available in this module. The shot test allows you to place different test points in the operating characteristic diagram. You can quickly confirm whether the operating characteristic is within the specified tolerance band. If you have a look at the characteristic in the diagram, you will notice that it changes depending on the selected fault type. This is called combined characteristic. Now we will see how it works. Let's take the following distribution of currents for a single-phase fault. We can see that the currents of the faulted phase are twice the currents of the non-faulted phases. The bias and differential currents can be calculated out of these values. Now we can locate these points in the diagram. The faulted phase will not lead to a trip. The test point falls within the blocking zone of the characteristic. However, the relay will trip because of the currents in the non-faulty phases. For this reason, the characteristic for the non-faulty phases has to be adapted in order to match the relay's behavior. The characteristics of the faulty and the non-faulty phases are then put together to get the resulting characteristic. The characteristic that you see in the operating characteristic diagram is adapted automatically to show whether you can expect a trip or not. We will now test a three-phase fault as an example. To test the slope of the characteristic, place one shot below and one shot above the start and the end of each segment of the characteristic. Place the shots close to the tolerance borders to check that the characteristic is correct in its limits. Use the available entry fields of bias and differential current to add test points or directly use the diagram for this purpose. Now we are ready to start the test and assess the results. It is possible that some test points turn pink during the execution of the test. This means that the point could not be tested because the test current exceeds either the test range of the connected CMC or the relay limits specified in the test object. To get more information about the icons, search for status icons in the Help section. You can only perform a search test or a shot test in this test module. Copy and paste the diff operating characteristic test module to keep your settings and to perform a search test. Also, only one fault loop can be tested in one module. You will need a separate module for each fault loop. The search test allows you to find the exact position of the operating characteristic. To insert a test line, enter the value for the bias current or right-click in the diagram. You can choose whether the nominal characteristic shall be ignored in the search test. If you check this box, the test module will search the characteristic of your relay along the test lines. If you do not check the box, the test module will only search the characteristic inside the tolerance borders. The resolution determines the accuracy of the search test. The test module will take the larger of the absolute and relative values for each test line. We can keep the default values for the resolution and start the test. As we can see, the search lines have been assessed as passed. As expected, the exact position of the characteristic is within the tolerance band. In this tutorial, we will introduce two test modules. diff trip time characteristic, and diff harmonic restraint. The diff trip time characteristic test module checks the trip time of the protection device. The diff harmonic restraint module tests the behavior of the differential protection for the harmonic restraint. Starting with the diff trip characteristic, verify that the current outputs and the trip signal are enabled in the local hardware configuration. The test view provides 4 tabs to parameterize the test. The binary outputs can be activated or deactivated from this tab. In this test module, you can use different tolerance values than those you specified in the real block differential. If you want to enter new tolerance values, check the Use Evaluations Factors box and fill out the entry fields below. Select Apply to enable the voltage output of the selected winding. In the General tab, you can define a pre-fault state and choose the trigger condition. In the Other Settings section, you can choose the windings to be tested. Keep in mind that the fault side is always assigned to the reference winding defined in the real block differential. Furthermore, you can set the test line slope, which represents the relationship between the differential and bias currents. Based on this value, Test Universe calculates the bias current for the test. In the operating characteristic diagram, the test line is displayed. Make sure that this line is above the line of the characteristic. This ensures that the trip time can be assessed. Usually, it is not necessary to change the default setting for the test line slope. In the Test tab, you place the shots to test the trip time. We will test a 3-phase fault as an example. The time tolerances are indicated by the red dashed lines in the trip time test plane. To define the test points, you can either enter the differential current in the entry field or right-click on the diagram to add a test point. If you want to add a series of points, use the Add Sweep option. In this case, you must define the start and end values. Enter the step size and add the points to the table. When the test is executed, the test module displays the trip times and evaluates them. We see that the relay trips faster if the test point is above the high set value. In this area, the relay trips independent of the bias current. Now it is time to open the diff harmonic restraint test module. Again, verify that the current outputs and the trip signal are enabled in the local hardware configuration. In a similar way to the other test modules, the General tab allows you to apply a post-fault, a voltage output, and change the trigger condition. In the diff harmonic restraint test module, you can perform a search test or a shot test. It is not possible to run both in the same test module, so we will show you the shot test first. This test makes an estimation of the blocking and non-blocking zones of the harmonic restraint function. We will do the shot test for the second harmonic. Usually, you can keep the default phase shift angle between the harmonic current and the differential current. If you want to use another value, enter it in the entry field. Enter the differential current and the harmonic ratio to add a test point or use the diagram. Place a shot next to the tolerances of the characteristic right at the beginning and the end of the line. In that way, you can test the slope of the harmonic restraint characteristic. Start the test to assess the test points. You can see the results for each test point. To perform a search test, we insert a new module in the OCC file. The search test allows you to find the exact position of the harmonic restraint characteristic. We perform the search test for the harmonic restraint characteristic of the fifth harmonic. To insert a test line, enter the value for the differential current or right-click into the diagram. You can also choose whether the nominal characteristic shall be ignored for the search test. If you check this box, the test module will search the characteristic of your relay along the test lines. If you do not check the box, the test module will only search the characteristic inside the tolerance borders. As expected, the exact position of the characteristic is within the tolerance band. Therefore, the search lines have been assessed as passed. Due to the high level of accuracy and stability of the CMC test sets, meter testing has become much easier. The use of reference meters is no longer required since the signal source itself becomes the reference. The CMC not only provides the test signals, but also allows for closed-loop testing. For optical meters, Omicron offers a variety of scanning heads to capture the pulses and incorporate them into the test assessment. The meter test module from Test Universe allows for manual or automated testing of energy meters. This video tutorial will guide you through the setup of the test module, including the test object and hardware configuration. For this purpose, we will test an ISKRA energy meter while using the CMC as a reference. We open the test module directly in standalone mode. According to Omicron's Ohm's law, we will enter the general device settings in the device block of the test object. As explained in previous videos, this block contains parameters such as name, manufacturer, and nominal values. We will assume that the meter is located in a 110 kV and 600 amps network. The secondary values are set according to the nominal values of the meter, that is, 400 volts and 5 amps. As we are using a dedicated test module, a new RIO block is also available. The meter block contains the specifications of the meter that are required for conducting the test. As we can see from the first drop-down menu, this module supports different meter functions, including, for instance, the measurement of active, reactive, and apparent power. Depending on the power flow definition, we have to indicate whether exporting should be considered from the point of view of the generator, that is 0 degrees, or from the point of view of the consumer, that is 180 degrees. Set this parameter according to the meter's configuration. When choosing one of the meter functions, it is necessary to specify the energy direction of the test according to our definition. In our particular case, we will check the energy in watt-hours from the generator's point of view. Now, we can choose from importing, exporting, or bidirectional. The power angle of the test will be adjusted depending on this selection. We will choose exporting, so the power angle will be set to 0 degrees by default. The test can be performed with any balanced or unbalanced load for single-phase, 3-wire, and 4-wire meters. Since the meter under test presents inputs for 3 phases plus neutral, we select the 4-wire option. The pulse type option can be set to active high or active low, which must match the meter under test in order to measure the pulse count accurately. Our meter under test counts on active high pulses, which is on the rising edge of the measured pulse. The CT and PT ratios are taken from the Rio block device. If it is necessary, go back to this block to modify these values. The meter constant is critical for the conversion of pulses into a measurable quantity of power. The meter constant can be entered into one of these fields either as a primary or secondary value. The remaining three fields are automatically populated according to the CT and PT ratios. The setting time allows the meter to establish a stable operating state. This way, the meter is able to perform a reliable and stable measurement. Search for this setting on the respective datasheet. For this test, we will keep the default value of 5 seconds. For the evaluation of the test results, the value for the tolerance has to be specified. This is done in the class field. In our example, the value will be set to 0.5. If you are testing old electromechanical meters, set the correlation between the rotation of the disc and the number of pulses. This factor and the meter constant are required in order to calculate the total amount of energy. Once all of the information has been input, we can confirm the dialog. The next step in Omicron's Ohm's law is the hardware configuration. We will choose to have 3 voltage outputs and 3 current outputs from the general configuration of the CMC test set. This particular meter includes binary outputs in addition to LEDs. This means that there is no need to use an optical scanning head since we can route one of the relay's outputs to one of the CMC's binary inputs. Therefore, we configured the first input to be a counter and we confirmed the dialog. Check out the next video tutorial to learn how to configure the meter test module. The meter test module comprises several views. The test view is composed of 2 tabs where you can define settings and test points. Starting from the Settings tab, we first define the measurement conditions. The drop-down menu allows the values to be set as either secondary or primary, where the CT and VT ratios are applied. The time sequence of a meter test starts with the warm-up time, where the nominal voltages are output. Next, the test begins the defined startup time. During this period, all the test parameters are output without starting the meter pulse recording. Keep in mind that this time cannot be lower than the setting time defined in the test object. This way, we can ensure that the meter stabilizes before starting any measurements. After this period, the time measurement for the meter under test is started. We can keep the default values for this example. Enter the ambient temperature and relative humidity. These values do not affect the test but will appear in the report. We will measure the active power that is being exported. This option is already selected in the measured quantity box while the remaining options are disabled. If a multifunction meter has been selected in the test object, you have to specify all of the quantities to be measured by clicking the respective options. As mentioned in the previous video, we will be using the CMC as a reference. However, you can still use an external reference meter as your reference. This reference meter's accuracy is then the reference accuracy for the error calculation. The reference meter data has to be specified, including the meter constant. This data can be updated, imported, and exported for later use. The Test tab contains the information for the test points to be executed. There are different test modes available depending on your application needs. In this example, we will apply a load test to check the meter's accuracy under normal operating conditions. The CMC test set outputs a set amount of energy until the meter feeds back the specified number of pulses. Check out the Help section if you want to see definitions for the other types of tests. In this test, we will output a pure sinusoidal current. Other current waveforms are available for testing the behavior of meters with harmonics or DC components. For a balanced three-phase system, you can specify the values of voltage, current, power angle, and frequency. Note that the power angle has been set to 0 since we will test the measured active power according to our definition in the test object. In the detail view, all parameters can be specified independently for each phase. Apparent, active, and reactive power are indicated for each phase and the complete three-phase system. The test quantities are displayed graphically in the phasor view by the voltage, current, and power vector diagrams. Now, you only have to define the test itself by entering one of the nominal values, that is, the total amount of pulses, the energy to be injected, or the test time. For example, we enter 5 pulses. The energy and total time are calculated automatically. The tolerance is set by default to the meter's class specified in the test object. The number of test runs specifies how often the selected line of the test table is executed. If you select the Pause Test checkbox, the currently selected test line is paused before being executed. Use the Define Trigger dialog box to define the message to be displayed when the test is paused. You also have to specify the trigger condition that will cause the paused test to continue. You can choose to have a button pressed condition, a binary input, or a combination of both. Now, run the test and check the results. The test line has been assessed as passed, as indicated by the green tick. Synchronizing relays are of great importance when it comes to ensuring a safe connection in a variety of switching operations. The principle behind these devices is simple. Synchronizing relays are able to measure 2 voltages with respect to phase angle, frequency, and magnitude in order to safeguard against the interconnection of 2 unsynchronized systems. For testing this type of relay, Test Universe includes the synchronizer module. In this video tutorial, we will test the active synchronization functionality when connecting a generator to the network. During the so-called active synchronization process, the relay uses control commands to adapt the amplitude and frequency of the generator voltage to the conditions of the network. At any moment, the synchronizing device is able to check whether the conditions for switching on the circuit breaker are being met. Once this is achieved, the relay issues a circuit breaker close command. If the conditions are not met within the maximum synchronization time, the process is aborted. The allowable amplitude, frequency, and angle deviations between the power system and the generator voltages are defined in the relay under test. The relay that will be tested in this example is the Siemens 7VE63. Since we are about to test a new relay type, we will open a new OCC file. This document will contain the synchronizer test module. According to Omicron's Ohm's law, we first configure the global test object. As usual, the device block will contain the general device settings such as the name, manufacturer, and nominal secondary values for the reference system. As you can see, a new real block is available to define the parameters of the synchronizing relay. The first tab contains some information about the systems that need to be synchronized. System 1 is always considered the reference system. Its values for secondary and primary nominal voltages are set in the device block. If the secondary voltage of System 2 differs from System 1, clear the Use Ratio of System 1 checkbox and input the corresponding value in the edit box underneath. Select the direction of the phase rotation and choose the voltages that need to be compared in the Connected Voltages drop-down menu. The CB closing time box shows the time that has been set in the CB configuration Rio block. This is the time between the output of the CB close command and the actual closing of the circuit breaker. The CB closing time is used to calculate the phase angle difference between the two systems at the time of the CB closure. The transformer group field allows you to specify any phase shift from a coupling transformer. The Start-Release drop-down menu specifies the type of signal that will be applied to the test object during the synchronization process. This option has to be set in accordance with the logic of the relay under test. You can choose from pulse, continuous, or none. The pulse option uses the start and release signals for attempting and aborting synchronization. The continuous option ensures that the start signal is output during the entire synchronization period, but no release signal is issued. The none option does not issue a signal during the process. In our example, we will compare the phase-to-phase voltages of both systems. We keep the same VT ratio for systems 1 and 2. The relay requires the use of start and release signals, so we will use the pulse option. The Synchronizing Window tab contains more details about the synchronizing characteristic of the relay. Since the magnitude, frequency, and phase of the voltages have to match in both systems, we need to specify the allowable range together with the tolerances in absolute and relative values. Some relays check that the synchronization conditions are met for a certain time. The minimum synchronizing time edit box is available for this purpose. Dead zones are areas where the relay will not output any control commands. The existence and size of the dead zones depends on the relay's configuration and its parameterization. When defined in the test object, they will be displayed in the test module. However, these zones are not assessed during the test. In other words, they serve as an aid for visualizing the relay's behavior but have no actual influence on the test. The Siemens 7VE63 has not been configured to have dead zones. For this reason, we will set them to 0. The relay settings are shown in the screen so we can enter the values. With regards to the hardware configuration, we choose a general configuration with 4 voltage outputs and no currents. For this test, we need 2 output voltages. One of them represents the phase-to-phase voltage of the network, while the other is the phase-to-phase voltage of the generator. Regarding the binary inputs, 4 of them will monitor the control command signals of the relay. That is, 2 signals can raise and lower the voltage magnitude, and 2 more signals can raise and lower the frequency. An additional binary input will be used to monitor the relay's circuit breaker close command. Finally, 2 binary outputs will be used as control signals for starting and aborting the synchronization. Now, we are ready to configure the test module. Check out the next video tutorial to learn how to configure the synchronizer test module. The synchronizer test module is composed of several views. The test view provides 4 tabs to parameterize the test. The sync view contains the relay's synchronization characteristic. It shows the difference in voltages versus the difference in frequency from System 1 and System 2. The test points will be depicted in this diagram. The synchronoscope displays the phase difference between System 1 and System 2. The solid green lines represent the allowable phase difference, while the green dashed lines symbolize the tolerances entered in the test object. When the test is started, the blue arrow rotates in order to show the phase difference that is being measured between the two systems. The higher the frequency difference between the two systems is, the higher the rate of change will be for the phase difference. The blue arrow stops when the relay issues the circuit breaker close command. A red arrow appears after the closing time to show when the circuit breaker is actually closed. The time signal view and the report view are available as in the other modules. Now we will focus on the settings of the test view. The Settings tab contains common testing parameters that are used by the different test modes, that is, function, adjustment, and auto test modes. During the pre-synchronization time, the voltages are output by the CMC test set, but no start signal is issued to the synchronizing relay. This allows the voltages to stabilize. At the end of the pre-synchronization time, the start signal is issued. The maximum synchronization time limits the amount of time for each test point. Only when the synchronization is achieved within this time can the test advance into the post-synchronization period. During this time period, the CMC test equipment continues to output voltages and it sends the release command. The minimum post-synchronization time that can be input depends on the start-release type defined in the test object. If set to continuous or none, the minimum post-synchronization time is the CB closing time. If set to pulse, as in our case, the minimum post-synchronization time is the higher value between the circuit breaker closing time and 500 milliseconds, which is the pulse duration issued by the synchronizer. If no synchronization is achieved, a release signal is sent to the relay and the test for this point is finished. The delay is the time in between 2 points during which no voltages are output. Once these time settings are entered, we can proceed with the first test. The Function tab checks the correct performance of the circuit breaker close command under different operating conditions. Based on the synchronization conditions defined in the test object, the module compares the nominal response that is expected with the actual behavior of the relay. As a result of this comparison, the test point is assessed as passed or failed. Remember to check the local hardware configuration before configuring the test module. To get points into the table, you can either use the input fields or add a point directly from the sync view. Use the Quick Test option to add a total of 8 points at the tolerance borders. This is a quick way to insert meaningful test points into the test table. We will use the Quick Test option, but we will shift the points where the frequency difference is 0. This is because the relay requires a certain frequency deviation to work properly. For the test points within the synchronizing window, the relay should issue the circuit breaker close command. For the outside points, the synchronization is not possible. Now we press play to run the sequence of test points. For each test point, the synchronoscope shows the relay's close signal and the moment that the circuit breaker is actually closed. Since it is not possible to run 2 different test modes in the same module, we must add an additional synchronizer module to the OCC file. This time, we will run the adjustment test. This test allows us to check the actuator commands issued from the relay to the generator. Do not forget to check the local hardware configuration to ensure that all signals are enabled. The principle behind the operation of the relay is to bring the generator into synchronization by means of the voltage and frequency control commands. The synchronizer test module detects these commands and changes the outputs in accordance with the generator model that has been previously defined. The relay has to issue the control signals until reaching synchronization conditions. During the controlling process, all points are driven to a specific target point inside the synchronizing window. This target point depends on the logic and configuration of the relay, in this case, 40 MHz and 0 volts. However, keep in mind that the relay will issue the close command as soon as all the conditions are met, whether the target point has been reached or not. The module will check that the time elapsed between the start signal and the CB close command is within the maximum synchronization time. At this point, we need to specify the mathematical model of the generator. It is used by the CMC to simulate the behavior of the generator when the relay issues actuator control commands. The synchronizer test module can work with the predefined generator models or user-defined models. In this example, the generator follows a linear model. The voltage and frequency change ratios are 4 volts per second and 150 millihertz per second. Now we add 4 test points to the table, all of them outside of the synchronizing window, and we start the test to assess the results. As we can see, the results are successful for all test points. Therefore, the conditions were met within the maximum synchronization time. In the sync view, you can trace the trajectory of each test point from the starting position to the moment that the relay issues the circuit breaker close command. Finally, remember to check the time signal view if you want to see and perform measurements on the recorded signals. Power quality has become an important issue because of the increasing sensitivity of electronic equipment and the high costs resulting from the loss of supply. Furthermore, structural changes in power generation result in a higher susceptibility of the power systems to malfunction. Therefore, the use of power quality analyzing devices is becoming more and more common. New regulations like the standard IEC 62586 are appearing to guide the testing and calibration of devices used to measure power quality. The Power Quality Signal Generator Test Module enables the generation of signals for simulating power quality phenomena with a CMC test set. It provides the entire functionality required to test power quality meters according to the new standard IEC 62586. To test a power quality meter, the CMC 256 Plus is the first choice because of its high accuracy. You can also use other CMC products like CMC 356 or CMC 353 if the accuracy requirements allow it. For example, to test Class S power quality meters. The PQ Signal Generator Test Module allows the definition of tests which consist of a sequence of individual test states. Each test state represents the output of a defined signal for a specified time to simulate a specific power quality phenomenon. The assessment of the meter's reaction to the applied signal can be done either manually or automatically. The results of the test are logged in the test report. In this tutorial, we will show you an example of a type test with the power quality signal generator module as it is done by the manufacturer or a certifying body. Doing so, we will perform one of the power frequency tests according to IEC 62586-2. The nominal frequency of the power quality meter under test is 50 Hz, while the nominal line-to-line voltage is 100 volts. The first step in the power frequency test is to check that the averaging interval is 10 seconds. That is, the frequency readings must be obtained every 10 seconds. According to the standard, we have to vary the frequency in a ramp as shown in the picture. The ramp lasts 10 seconds. Its highest value is 57.5 Hz, and the lowest 42.5 Hz. Keep in mind that these values are only correct for a 50 Hz power quality meter. According to the test criteria of the standard, the value measured every 10 seconds shall stay the same within twice the intrinsic uncertainty of the meter. Furthermore, the total number of frequency readings must be 11, 12, or 13 in 2 minutes. We will use a new OCC file to perform this test. The information in the test object must be completed prior to the test. For the power frequency test, we enter a nominal frequency of 57.5 Hz. The reason for choosing this value will be explained later in this video. The nominal primary line-to-line voltage is 110 kV, while the secondary voltage is 100 volts. The current ratio is 600 amps to 1 amp. The global hardware configuration allows you to define the inputs and outputs of the CMC that need to be used. We require 3 voltages and 3 currents to perform this test. Remember to perform a wiring check before proceeding with the test. Now we insert the power quality signal generator test module to conduct the power frequency test. The test view allows you to specify the states used for the test. At the beginning, there is only one test state by default. Go to the States tab to insert a new state according to your needs. The signal type can be chosen from the drop-down menu. These signal types are set in accordance to IEC 61000. You can also use the Quick Insert button and change the signal type in the test view. All test states can be renamed accordingly. Since IEC 62586 specifies that the power frequency test must last 2 minutes, we can execute the ramp 12 times to match the specification. This can be done by entering the right value into the number of loops field. The detail view contains the specific parameter settings of the test state that is selected in the test view. Accordingly, the content of the detail view depends on the signal type of the selected test state. Use the Help menu to learn more about the detail view configuration of a specific signal type. The upper area of the detail view holds the specification of the incident times and the voltage or current channels that the signal is applied to. In order to set the incident times, it is necessary to take a few facts into account. Since we want the ramp to start immediately and to be repeated afterwards, the pre-incident and post-incident times can be set to 0 in this case. For the power frequency test, one can see that the incident time will be on the tip of the triangle. Therefore, we can assign the shortest time possible, which is 1 millisecond. The nominal voltage is linked to the value specified in the test object. The reason for entering a frequency of 57.5 Hz in the test object becomes clear at this point. The upper limit of our ramp is set to this value by default. Use the checkboxes to select which voltage channels you want to apply the signal to. A box that is unchecked does not imply that the output is deactivated. It only means that the nominal voltage will be output at this channel. Remember that any output can be deactivated from the hardware configuration. The lower part of the detail view contains additional settings of the ramp. The incident value is the minimum value reached by the ramp. In our case, it is 42.5 Hz. The purple background of the voltage indicates that the value is linked to the nominal value specified in the Rio block. Each ramp takes 5 seconds, which makes a total of 10 seconds for the two ramps. The threshold value is the value where the power quality meter should detect the incident. Since we do not want the meter to detect an incident, but to check the averaging interval, the threshold value is not required. Therefore, it can be set to any point below the incident value. Anyway, the threshold value is only a graphical representation, and it will not influence the test. In the General tab at the Detail view, you can choose a binary input for the automatic assessment of the test. Just check the binary input box and select the signal from the drop-down menu. Remember that the signals must be enabled in the hardware configuration. This option requires a meter that provides you with binary outputs for the assessment. In this example, we will proceed with a manual assessment so that no binary inputs are required. You can also define the state of the post-incident binary outputs. They can be set to open or closed during the post-incident time of the state. Furthermore, you can define the magnitude and phase of the current outputs. For the manual assessment of the test, it is necessary to insert an assessment state. The two test states are grouped together by default, which means that both states will be repeated according to the number of loops specified in the entry field. Since only one assessment is required, you can use the split button at the States tab to segregate the assessment from the power frequency test. Likewise, you can use the Merge button to group the selected test states. As the assessment state is meant for manual assessments, you can include an instruction for the tester in the Detail view. For instance, we can define an instruction according to the requirements and specifications of the standard. If you want to repeat all tests, you can enter the number of repetitions in the overall loops entry field. A wait state can also be used to apply nominal values during the test sequence and to pause the test sequence. You can define a maximum wait time or continue the test manually. Starting the test causes the test progress window to open. This window provides you with detailed information about the test sequence, estimated time for each state, states count, and current state information. With the Highlight Current State box, you can see the current state in the test view. By reading out the values from the power quality meter, we can assess the test according to the specified instruction. In this example, we have checked a total of 12 readings. You can enter any result in the comment field. Since the frequency of all measurements is within the intrinsic uncertainty, we can assess the test as passed. Now we have finished the very first test of the power frequency tests according to IEC 62586-2. To save time for preparing such tests, Omicron provides you with a number of templates for testing power quality devices according to the standard requirements. These templates are accessible from the Test Universe start page and are stored as OCC files on your hard disk. Instead of building your own OCC file from scratch, we will show you how to use these templates. The available templates have been designed for power quality meters that operate with nominal values of 60 Hz and 120 volts. A meter with different nominal voltage or frequency requires an adjustment of the corresponding values. We can take the template for the power frequency as an example. The different modules in the OCC template include a pause module to describe the tests that will be conducted. Prior to the adaptation of the template, save it with a new name in the folder of your choice. Doing so, you make sure that the original template will not be modified. We start off by entering the voltage and frequency settings for this example. That is 50 Hz and 100 volts. The capabilities of the power quality signal generator test module are many. For instance, you can test the variations due to single influence quantities. This test is specified in section 1.3 of the standard. With this test, you can check the influence of the voltage and of the harmonics on the measurement uncertainty. The local hardware configuration must be checked before the module is configured. The multi-incident signal type is used to generate any combination of the signals available, which turns out to be a perfect solution for this test. This signal type can combine power, frequency, flicker, voltage unbalance, harmonics, and interharmonics. Each of these signal types can be individually parameterized according to your needs. In the first multi-incident test state, the signal types power frequency and voltage unbalanced are combined. Since the template has been created for 60 Hz, it is necessary to adapt the related values. The incident value of the frequency must be changed according to the standard. The voltage must be set to 10% of the declared input voltage. In our case, this is 10 volts. In the second multi-incident test state, the influence of the harmonics are tested. Therefore, the signal types power frequency and harmonics are combined. The frequency incident value must be adapted as in the previous case. The harmonics do not require any adjustment since they are relative values that refer to the nominal voltage of the fundamental. Remember that this voltage was set in the test object. Transducers are devices that convert one form of energy into another. They are used across industry sectors for measurement and control and are designed to monitor currents, voltages, power, phase angles, or frequencies. Some programmable multifunctional transducers are capable of acquiring multiple input quantities simultaneously. The transducer converts these inputs into a proportional analog signal. The transducer test module enables the CMC test set for manual or automatic testing of any measurement function, such as real power, phase angle, or frequency. The video tutorial will walk you through the configuration of the test object. We will use a Siemens 7KG6000 as the test object for this example. We begin by inserting a transducer test module into a new OCC test document. Use the device block from the test object to enter general information, such as name, manufacturer, or nominal values for primary and secondary. If the VT and CT ratios are entered, you will be able to work either with secondary or primary values in the test module. The transducer block contains the test object parameters for conducting the test. Use the checkboxes in the transducer functions list to select those that are active for the transducer under test. The selected functions are included as tabs in the lower section. Although you can check more than one function for multifunctional transducers, keep in mind that only one function can be tested at a time in one test module. This can be solved easily by embedding multiple test modules in the OCC test document. To keep it simple, we will only test the transducer's voltage measurement function. The other functions can be tested in a similar way. Start off by defining whether the transducer output is DC voltage or DC current. The open loop option is available for those transducers that output the result in a display. In the test module, a pop-up dialog allows you to enter the transducer's reading. The angle calculation determines how the transducer measures the power system phase angle. Either the voltage or the current can be taken as a reference, resulting in positive or negative values. Make sure that you match the setting of your transducer. The full-scale error reference, which is the difference between maximum and minimum value, is used to calculate the device error. This value will be compared with the specified tolerance value for the assessment of each test point. This selection is only available when a symmetrical characteristic is chosen. Otherwise, the option 0 to the maximum value is selected by default. Similar to other test modules, we need to specify the CT star point connection, direction line, or direction bus bar. Remember that forward direction is defined as active power flow from the bus bar towards the line. The setting time elapses before the measurement at the analog input is taken. This time has to be set in accordance with the transducer datasheet. This ensures a reliable test result. For this particular test, the default value of 1 second will suffice. Now it is time to define the characteristic of our transducer. First, select the number of phases that the transducer operates. The availability of this selection depends on the specific function. For instance, while this is a free choice setting for the active power test, it is fixed for the current measurement function. The tolerance option specifies the maximum device error for a specific test quantity. If a multifunctional transducer was chosen, it is possible to define a specific tolerance for each of the functions. Refer to the manual to verify this value. In our particular case, the transducer presents a tolerance of 0.5%. The characteristic definition offers the selection of either linear, compound, or quadratic options. In addition, should the transducer be complex in nature, there is a checkbox for symmetrical characteristic behavior, which is typical for bidirectional power transducers. The transducer input range for the voltage measurement function is from 0 to 90 volts, while the transducer output range is from 0 to 20 milliamps. Of course, the transducer output has to be set to DC current. According to the transducer settings, the saturation range or limit of the characteristic is 22 milliamps. Make sure that the test range lies within the saturation range. Now we need to configure the hardware connections accordingly. We will use the voltage outputs of the CMC as well as the analog DC current input. The transducer test module is organized in several views for easy testing and the easy assessment of results. As a first step, remember to check the local hardware configuration. Make sure that you have the correct outputs and inputs assigned to perform this test. The test view comprises 3 different tabs to parameterize the test. Going from right to left, the first tab contains common settings that apply to all the specified test points. If multiple functions have been defined in the test object, it is necessary to select the one to be tested. Remember that only one function at a time can be tested. The test points can be specified in primary or secondary values. To keep it simple, we will use secondary values in this example. The test mode presents two options. Auto-stepping is selected by default. It simply means that the test points are executed automatically in the same order as they were added to the table. Manual stepping gives you the opportunity to manually confirm the execution of each test point. A dialog box pops up for this purpose. In principle, all executed points will be displayed in the transducer's characteristic of the test view. This is the default setting. However, you can decide to only see the failed points. If you have a measurement device with no separate auxiliary power supply that is energized by the connected voltages, just check this box. The CMC will inject nominal voltages in all the phases that are not being subjected to the test. Since voltage is always a single-phase test, we have to select the phase to be tested. For instance, we choose phase 1 in this example. Enter the ambient temperature and the relative humidity that exists during the test. These two values will appear later in the test report. The Sweep tab allows you to test the measurement stability through a sequence of test points with equal step size. You can either define a voltage or a frequency sweep. The availability depends on the function that is tested. In fact, since we are testing the voltage measurement, only the frequency sweep is available. The input value will be applied to each test point of the sweep. In other words, this value will be kept constant while the frequency changes. Enter the sweep parameters, start, end, and number of points, to finish the configuration of the test. As we see in the simulation, the sweep is evaluated as a whole, and the result is displayed as a status icon in this field. Now we go straight to the Test tab, which is used for inserting individual test points. This can be done manually by entering the input value or by directly adding a point from the graph. An alternative and faster way of doing this is by using the Add Multiple option. This launches a sequence definition dialog where a maximum of 250 test points can be defined. For example, we can add 10 points from the range of 0 to 90 volts. Once we confirm the dialog, the test table is available. The test run specifies the number of times that a measurement is taken at a particular test point. If you choose 2 or more test runs per point, the average error and the standard deviation are displayed in the table and the test report. For each test point, you can have a look at the detail view. This section contains the data entry fields for the output generators and the resulting power. The availability of the fields depends on the function being tested. If any value is changed, all the related values are modified accordingly. For example, if the power is changed, the respective current is recalculated to match the power at a given power angle. It is also possible to apply a pure sinusoidal waveform or superimpose either a DC component or harmonics. Now we are ready to start the test and check the results. After the test is completed, the transducer test module provides error curves for the absolute error, relative error, and the device error.
In this tutorial, you will learn how to use the Advanced Power module to test the power criterion of the QV protection. The role of the reactive power direction and undervoltage protection, also known as the QV protection, is to disconnect decentralized power plants from the grid if they begin to behave in a way that is not compatible with the system stability after a grid fault. The QV protection device, therefore, monitors the voltages and reactive power direction. The protection device trips when all phase-to-phase voltages fall under a certain value in case of a fault and the power plant is drawing inductive reactive power from the grid at the same time. When it comes to the power criterion, there are two different types of characteristic. With variant 1, the trip range is defined using a reactive power characteristic. In addition, a minimum current criterion prevents erroneous tripping at very low power values. Variant 2 uses a reactive power threshold. You can test both characteristics using the advanced power module. In this example, we will be testing a QV protection device using an angle characteristic. The angle is set to 3 degrees. The protection device uses the load reference arrow system. The set value for the undervoltage threshold is 85% of the nominal voltage and the minimum current is 100 milliamps. The trip time is 0.5 seconds. Our Control Center file already contains some test modules used to test other QV protection criteria. The next thing we need to do is add an advanced power module to test the power characteristic. The advanced power module offers two options for testing in the power plane, the shot test and the ramp test. Both modes offer the possibility of using characteristics defined in the power plane for the test. At the moment, no characteristic is being displayed here, as no characteristic has been added to the test object. We will therefore begin by configuring the test object. The Rio block power has all relevant parameters for the power test ready to be defined. In the Systems Setting tab, we first enter the general parameters. In our example, the star point of the current transformer is set to towards line. Make sure that this setting matches the corresponding setting in the protection device, as it has a significant influence on the power direction. The reference power is required for relative power data. As we are only using absolute powers, the reference power is not relevant for us. In this example, the time tolerance should be 60 milliseconds. For the angle characteristic, the power tolerance is taken from the power angle tolerance. It is 2 degrees. The values for tolerance S absolute and tolerance S relative can be set to 0. The next two sections can be used to define additional voltage and current thresholds. They will be considered during the test. In our example, we will define the minimum current criterion as an overcurrent threshold. The set value of the minimum current is 100 milliamps, and the tolerance is 2% of the nominal current, which is 20 milliamps. The undervoltage criterion will be considered later in our test by defining a constant test voltage of 85% of the nominal voltage. However, we enter a value here to allow for an automated assessment of the test module. If we do a cross-check with a higher voltage value, then the relay should not trip. In the next step, we will enter the power characteristic. First, we enter a new trip zone. Double-clicking on the table entry will open the Characteristic Editor. Here we can add a predefined zone. We need a blinder of 3 degrees. The minimum reactive power is 0 var. If your protection device uses variant 2, the reactive power threshold, you can enter the characteristic following the same principle. Simply enter the value of the threshold into the min-Q field. In this case, the angle is 0. To finish defining the characteristic, we enter the nominal trip time of the zone. In the next step, we will configure the hardware. For the test, we require 3 voltages and 3 currents. We select the trip as the signal in binary input 1. We do not require any binary outputs for the test. Now we can set up our test. In the Test Settings tab, we select the test model. As we must ensure that the undervoltage criterion is always met during the tests, we select Constant Test Voltage. For the value, we need to enter a voltage that is less than 85% of the nominal voltage and outside of the voltage tolerance, for example, 82%. We then set the duration of both the pre-incident and reset states to 1 second. The reset state is output after every ramp to ensure that the protection device resets. It is important to ensure that the currents and voltages in both states are not within the trip range. The maximum incident duration is only relevant for shot tests and not for ramps. Now we define the power ramps in order to test the characteristic. The characteristic is indicated by the blue line on the power diagram. The red circle results from the minimum current criterion. To test the characteristic, we will define a total of 4 ramps, 2 ramps for active power generation and 2 ramps for active power drawing. It is important to ensure that the test currents are above the minimum current. We first select incident type ABC as the QV protection only trips when all 3 of the phase-to-phase voltages drop. Under ramp mode, we select S-Phi. We begin the first ramp at a test current of 300 milliamps. Initially, the angle of the apparent power is 180 degrees. The ramp ends at an angle of 170 degrees. The test current should remain unchanged at 300 milliamps. During the test, the phi angle should be gradually altered in steps of minus 0.5 degrees. The duration of the individual steps should be 1 second, which is double the trip time. Click on the Append Ramp button to add the ramp to the test. Now we define a similar ramp for a test current of 800 milliamps. To do this, we right-click on the first ramp to copy it and then subsequently paste it. Then we change the test current for the start and end values accordingly. Now we paste the first ramp once again and change the power angle so we can test the characteristic for active power drawing. The ramp now runs incrementally from 0 degrees to 10 degrees. We copy this ramp once again for a current of 800 milliamps. The 4 ramps are also displayed in the power plane. In the last step, we define the assessments. The first assessment is carried out for ramp 1. The measurement takes place at the point in time in which the trip signal changes from 0 to 1. We measure the phi angle. The nominal value is 177 degrees. The permissible deviation is 2 degrees. Now we copy the assessment so that we can use it for the second ramp. The angle of the second ramp must also be 177 degrees in accordance with the characteristic. For the third and fourth ramp, the nominal value is 3 degrees respectively. Now we can start the test. As usual, the test results can be viewed in the module itself and in the report. This concludes the test of the QV protection power characteristic. Please note that additional tests are required for a complete test of the QV protection. For example, an additional advanced power module can be added that contains a ramp at a constant test voltage above the undervoltage threshold in the reactive power trip range. In this case, the protection device must not trip. The test module examines the behavior of the protection device by using the values in the test object and automatically checks that the protection device has not tripped. In this tutorial, you will learn how to test the pickup value and the trip time of the reverse power generator protection function. Conventional testing of generator protection functions is a big challenge. Without having a proper PQ plane to work with, it needs a lot of imagination and calculations to test all power protection functions. Additionally, you need a lot of different test modules to set up your test. Typical generator protection relay characteristics for reverse power protection are defined as boundaries in the PQ plane. For a convenient way of testing and assessing the relay settings, a graphical illustration of the characteristic, as well as a visual definition of the test shots and ramps in the PQ plane, would be very helpful. Those needs are met by the test modules Power and Advanced Power, which make testing power protection functions much easier and visual. In this tutorial, we will use the Advanced Power module. In our example, we test the reverse power generator protection function. The nominal power is 173 watt and the pickup value is 3% of the nominal value, which is 5.2 watt. The angle phi of the power characteristic is set to 0 degree and the trip time is 1 second. We have already prepared an OCC document with the test object and a hardware configuration. For testing the reverse power function, we create a new group in the OCC file and insert an Advanced Power module. The Advanced Power module offers two options for testing in the power plane: the shot test and the ramp test. We will begin by configuring the test object with special attention to the Rio block for power protection. This Rio block Power comprises two tabs, one for general settings and the other one for defining the zones in the PQ plane. Let's start with the System Settings tab. In the upper part, we define the CT star point connection and the reference for relative power. Make sure to set the CT star point connection as it is in the relay, because it is essential for the power direction. The tolerances for power and time are required for the test assessments. They vary depending on the relay and are specified in the manual. The absolute and relative tolerances can each be defined, but the larger of the values is dynamically applied. If the relay manual does not state an angle tolerance, you may start off using the default setting in the test object. Some power protection functions are only active for a certain voltage or current range. In this case, a voltage and a current threshold can be set to allow for an automated assessment by the test module. In the Zone Settings tab, the zone characteristics can be defined. The Zones table contains a listing of all defined zones for all known zone types. We add a new trip zone to define the reverse power area. To simplify entering the settings, some common characteristic shapes are available as predefined types. We choose the percentage shape type. As zone orientation, we select -P. In this case, the blinder is 0 degree and the minimum value of P is 3%. To finish defining the characteristic, we enter the nominal trip time of the zone, adding the minimum operating time of the relay under test. Besides tripping zones, you can also define zones of the type Show Only, Do Not Test, and Alarm. For example, you can use a Show Only zone to display the generator capability curve during the test. Such a curve can be drawn using lines and segments. In the next step, we will configure the hardware. For the test, we require 3 voltages and 3 currents. We assign a trip contact of the relay to binary input 1, as trip zones expect a binary input assigned to trip. In addition, we assign the start contact to detect when the relay picks up. If you had also defined an alarm zone, it would expect a trigger signal at the binary input assigned to alarm. We do not require any binary outputs for the test. Now we can set up the tests. The Advanced Power module offers 3 tabs to set up the tests. In the Test Settings tab, we specify general test settings. We select either constant test voltage or constant test current as test model and specify its value as VTest or ITest. The respective other value is calculated by the test module and limited by the parameter Imax or Vmax. For our test, we select constant test voltage. In the Times section, the durations regarding shots and ramps are defined. The pre-incident duration applies to shots and ramps alike. We set the pre-incident duration to 1 second. It should be set to 0 if you do not want any pre-incident output. The max incident time applies to shots only. It defines the maximum output time the test module waits to be sure that no trip or alarm occurs when the zone settings do not allow any. In our example, the trip time is 1 second, so we enter a longer time here. The reset time defines the duration of a reset state, which is output between single shots as well as between ramps. Set it to 0 if you do not want a reset state. In this case, shots and ramps directly follow each other. At the bottom of the Test Settings tab, define the output values for both the pre-incident and the reset state. It is important to ensure that the currents and voltages in both states are not within the trip range. A mirrored current is a current that is identical to the defined reference current in waveform, phase, and frequency, but with an inverted and possibly scaled amplitude. This feature works for shot tests and can be used when testing a particular function of a multifunctional relay with an integrated differential protection feature. In this case, the mirrored currents setting ensures that this differential protection feature does not cause tripping. The first current triplet of the CMC then represents the current fed into the differential protection relay, whereas the second current triplet represents the current leaving the differential protection relay. Note that you can also define a factor for CTs with differing ratios at both protection ends. This setting allows for positive or negative values less than or greater than 1. For testing the pickup value of the reverse power function, we define a power ramp in the Power Ramps tab. We choose the incident type L1, L2, L3, the ramp type Step, and the mode PQ. We define the beginning and end of the ramp in the From and To sections. We start from 80% until 120% of the expected pickup value. Don't forget to set the angle phi to 180 degrees to simulate the reverse direction of power. Delta can be entered as a pure power P with a value of 1% of the expected pickup value, and the step duration should be longer than the inherent operating time of the relay. Note that the Advanced Power module offers a faster alternative that can be used for a quick check. When selecting the ramp type Smooth, the delta value and the step duration are calculated automatically. Don't forget to click the Append Ramp button to add the ramp to the table. The ramp is also being displayed in the complex PQ plane. We add 2 more ramps to test the pickup value for different reactive power values. In the Assessment view, we add an assessment for each ramp. We start with the first ramp. The measurement takes place at the point in time in which the start signal changes from 0 to 1. We measure the power P. The nominal value is 5.2 watt and the permissible deviation is 300 milliwatt. In the same way, we define the assessments for the remaining 2 ramps. In the last step, we will test the trip time with a shot test. You can define a shot either by simply clicking into the PQ plane or by entering the shot values manually. We will demonstrate the manual input option. As incident type, we choose L1, L2, L3 with a reverse power higher than the set value. The power can be defined as active, reactive, or total power with angle phi. The respective other fields are calculated automatically. Click Append Shot to add the shot to the table. The shot is also displayed in the PQ plane. In the Zone Assessments view, the assessment for the power shot is shown. It is defined automatically according to the settings from the test object. Now we can start the test. As usual, the test results can be viewed in the module itself and in the report.